So far we've looked at Newton's first law, which says an object's acceleration is zero if the force is zero, which is really just a special case of Newton's second law, which says net force equals mass times acceleration, right? If the net force is zero, the acceleration is zero. That's Newton's first law. Newton's second law just gives us the mathematical equation for that. Those two laws are very different than the third law, because the first and second law refer to one force acting on one object, but Newton's third law involves two forces, right? Remember, a force is always caused by an agent, but it turns out forces don't exist in isolation. We have the agent that causes them, but when two things hit, one object exerts a force on a second, but that second object exerts that same amount of force back on the first. So Newton's third law is actually a little bit long to write down. It states that when one object exerts a force on a second object, the second object exerts an equal force back on the first object. Now, this is, like I said, very different than Newton's first law, because Newton's first and second law were both about one object. Newton's third law is about two, and this is why labeling forces with the agents that cause them is very important, and drawing your pictures with the forces acting on the objects correctly is important. If we imagine for a minute that two people are having, I don't know, a little bit of a pushing match standing on ice. Usually I say let's draw people as boxes, but today I'm drawing people, kind of. Okay? There's my two people. They're pushing on each other. This person over here, I'm going to call this person on the left person 1, and this person on the right person 2. Person 1 is exerting a force on person 2. So person 1 exerts a force this way. And so I would call this the force of person 1. But because person 1 pushed person 2, there is an automatic push back on person 1. That force is the force from person 2. And this force are equal in size but opposite in direction. That's Newton's third law. Two objects, two forces, acting on different objects. So these are called action-reaction pairs, and it's important to note that action-reaction pairs act on different objects. One of my favorite questions to ask is, if Newton's third law says for every force there's an equal and opposite reaction force, how come anything can ever accelerate ever? Shouldn't every force just automatically be canceled? And that's because for every force there's an equal and opposite reaction force is incomplete. It's a poor statement of Newton's third law. Mine is longer, mine is wordier, but mine is correct. Mine says one object exerts a force on a second object, the second object exerts an equal force back on the first object. The reason action-reaction pairs do not cancel is because they do not act on the same object. So what happens to these two things? Well, they move apart. Person 2 here is going to accelerate this direction. Person 1 is going to accelerate this direction. So if you push each other on ice, you'll slide apart from each other. And you don't have to push each other this could all be initiated by person 1. But as soon as person 1 pushes on person 2, there's an automatic reaction force back on person 1. Same size force, but it acts in the opposite direction. Does that mean these two things will have the same change in motion? No, because force is not acceleration, force causes acceleration. So the best way I think to illustrate this is with an example of, say, bumper cars. So let's say I have one bumper car and it has a mass of 100 kilograms, and I have another bumper car and it has a mass of 50 kilograms. Okay, so I've got two different sized bumper cars, a bigger one and a smaller one, and they are going to hit each other. They're going to smash into each other. And you'll notice I did not draw them in contact because I want to remind myself that they are two separate objects. But let's say they collide with each other. As soon as that happens, they're going to exert equal forces on each other. And let's say that force is 400 newtons. So I've got a 400 Newton force this way, and I've got a 400 Newton force this way. And what I'm interested in knowing is how much does each one accelerate? Well, if that's the only force, and my picture doesn't show any other forces, so I'm going to go with that's the net force, then object 1 over here has a whole different set of numbers than object 2 over here. So it's important to remember that to the left is negative, so I can say, all right, well the net force on this one is actually negative 400 newtons because of that picture, it's to the left. Its mass is equal to 100 kilograms, so if I want its acceleration, all I have to do is Newton's second law. Net force equals mass times acceleration, and so negative 400 equals 100 times a, divide both sides by 100, and what we end up with is an acceleration of negative 4 meters per second per second. Okay, so this bigger car is going to accelerate to the left at a rate of negative 4 meters per second per second. However, if we do the same application over here on the right side, the net force over here is 400 newtons. It's positive, right, because it's an opposite force in the opposite direction. Mass over here is 50 kilograms, which means my acceleration is going to be different, right? That's Newton's second law again. Net force equals mass times acceleration. So 400 equals 50 times a, divide both sides by 50, and I get an acceleration of 8 meters per second, which makes perfect sense. If it's got half the mass, it'll have twice the acceleration. Its motion changes a heck of a lot more. Equal forces only cause equal accelerations on equal masses. If I have unequal masses, then I have unequal inertias, and it's easier to change the 50 kilogram cart's motion because it has less inertia. The math bears that out, and it agrees with what we know in real life. If we have a big truck moving down the interstate and it collides with a small car, the forces on both vehicles are the same, but the acceleration in the car is much greater because it has much less mass, which means the truck is basically going to continue doing what it's doing and the car is not. So it is better to be in the more massive vehicle in the car accident, not because there's less force, but because there's less acceleration.